Hello everybody, welcome back to Chemistry First Day. We are on the periodic table now, okay? It's a very important topic, okay? But easy to understand. We'll spend a few weeks on it, okay? Hope we can fully understand the trend in periodic table today. So first of all, we are on the periodic table, okay? Let's talk about structure of the periodic table. First, you have to remember what's a group number and period number, okay? And the periodic table consists of period, groups, and blocks, okay? We'll learn them clearly one by one. The period numbers shows the outermost shell electrons level being occupied. So equal 1, 2, 3, 4, 5, 6, 7 means a number of electron energy level being occupied. And element in the period n has n main energy levels and equal 1, 2, 3, 4, 7, 10. And element in the same groups has the same number of valence electrons, same number of outermost shell electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8 outermost shell electrons for different groups. And for group 1 and 2, we call it S block because its outermost shell electron is the S electron. And for group 13 to 18, we call it P blocks because its outermost shell electron is the P electron. And the 3 to 12 is we call it D blocks. Okay, it's a transition metal. And lanthanide and actinide is the two F blocks. So we seldom talk about them, but we have to know their existence. And we have different names for different group. For example, group 1 we call it alkaline metal, and group 3 to 12 we call it transition metal, and group 17 we call it halogen, and group 18 we call it a noble gas. And metals, okay, and non-metals. Metals are elements on the left of the periodic table, so they are S block, okay, D block and F block elements. And non-metal are on the upper right of the periodic table, they are P blocks elements. And metalloids are those between them, intermediate between metal and non-metal. For example, boron, silicon, germanium, arsenide, and so forth, okay. And before the isolation of William, there is a hole in the periodic table of atomic number 75. This is a good cue. Okay, scientists focus on it and isolate RE at last. Okay, so the whole periodic table is found. And don't panic, you'll find periodic table clearly in the data booklet, and lots of data are presented in the table of periodic table. And first is atomic and ionic radius trend. Okay, in periodic table. Periodicity refers to the trend in properties of element across a period and a down a group. So two concepts, across a period and down a group. Okay. Across the period from left to right means the same period, okay, but different number of groups, okay. And the concept is when we move from left to right, same number of shell, right, and same shielding, but the number of proton increases, okay. So there's a stronger pull of the outermost shell electron. This is the cruise for everything explained by the same concept. More proton, more pull. So the outermost shell electron is closer to the stable orbit, so stable, and then closer to the nucleus, so the atomic radius decreases in general. But there's a jump, okay. When you have a new suborbit P, okay. So down the group, when you're going down the group, the number of occupied electron shell increases, the atomic radius increases. And then we talk about ionic radius. Very easy, just add a +1 and -1 to it. But in general, they are a little bit different. So for the +1 because they have more proton, right? Yes, there are less electron, right? +1, one less electron, same number of proton, but one less electron. So the electron repulsion will be less electron, less, okay? So the ionic radius will be shorter. But for the -1, they have one more electron. So more electron repulsion. So the ionic radius should be longer. So they're longer and shorter in general. And for the same number of electrons, okay, for the isoelectronic ions, okay, the higher the atomic number, the more attractive force between the electrons and the nucleus with more proton. Okay. So shorter ionic radius for the Mg2 plus and O2 plus same electron configuration, but Mg has more protons, so more attraction force. So this one has a shorter ionic radius. Okay. Exception. When newer subshell appears, okay, the atomic ionic radius increases. So suddenly when the p shell appears, so look for the p shell. If it appears, then it will be a rise in the atomic and ionic radius. You can see the trend. The general trend is going down. Going down. It's a general trend for the atomic radius. You can find it out at table 10. Okay. And then the property across the periodic table, we got the electronegativity. Do you remember what's this? Yes, it's the ability to attract electron in a covalent bond. Okay. They want electron or not. Okay. For the electron element in group 18I is a complete octet already. The tendency to accept more electron is lower, so its electronegativity is smallest. Okay. And across the period from left to right. Okay. Remember the rules, okay? Same number of shells, same shielding, but number of proton increases. So the outermost shell electron is closer to the stable orbit, and the element has a higher tendency to accept more electron to form the stable orbit. So electronegativity increases. But down the globe, what happened? Far away from the nucleus, so attractive force decreases, so less tendency to accept more electron. Okay, so electronegativity drops. Okay, always the same concept. And property across the periodic table, we got the first ionization energy. First ionization energy is the minimum energy required, positive energy. Okay, required to remove one electron from gaseous state in the data booklet. Okay, is expressed in a mole, 1 mole of them. Okay. And first ionization energy, the energy required to remove an electron from an element. Okay, across the period, the same concept again. You see, same number of shells, same shielding, but as number of proton increases, right? So the outermost shell electron is closer to the stable octet too. Okay, harder to remove is so higher ionization energy. But down the globe, far away, less attractive force, weaker, so smaller, lower first ionization energy. And what is the exceptionally high one if they have a complete octet already? So the ionization energy will be very high because they are both stable. On the other hand, if they have a 1 electron more, they really want to kick it out, right? So the first ionization, next ionization energy will be lowest. Highest and lowest distinguish them. Think about whether they have a complete octet or 1 more electron than the complete octet. Okay, the other concept is the first electron affinity is different because when an atom absorbs an electron, energy is released. The energy change is negative. Be careful. The energy change when an electron is added to an element. Okay, but the concept is the same. Okay? Across the period, same number of shells, same shielding, number of proton increases closer to the stable octet. Okay, higher tendency to accept extra electron. So more energy is released. But be careful. More is released, so more negative, so decrease. Be careful. More negative is decreases. If you owe people more money, you are poor, right? Be careful. More negative decreases. But down the globe, the same concept. Far away, less attractive force. So fewer energy is released, so less negative and increase. Less negative is increase. Be careful. It's exception. For other trend, all the number is positive, except for electron affinity, the number is negative. So more negative is decrease. Be careful. So for metal has a delocalized electron seal. Right? So electron can be removed and added to metal easily. So the low ionization energy, electron affinity, both of them are loaded in metal. And you can see from the table number 9, okay, data booklet number 9, okay. First ionization energy, electron affinity energy are there, okay. And you see positive is the ionization energy, negative is the electron affinity. You can see the trend, okay, clearly going up, 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 up. And then the melting point is another property, but the same concept. Okay? Melting point depends on the type of bonding of the element because the metal has strong metallic bond and non-metal has weak van der Waals attraction, right? So the melting point for metal is much higher. And across the period, first the metal has more free electron, right? So the metallic bond increases, so melting point increases first. Okay? But the melting point later on will drop sharply when it goes to non-metal. So non-metal, metal, sharp drops. Okay. And down the globe is different idea. Okay. Down the globe, the number of occupied electron shell increases. So for metal, the free electron is far away from the nucleus. So the attraction force decreases, so the melting point decreases. But the non-metal, van der Waals force, remember, depends on what? Number of electron. More electron, more randomness probability, right? So more easily to be polarized, okay? Random polarized, okay? So the randomized force increases, so the melting point increases, so down decrease, down increase, okay? So there is a crossover there, okay? For metal and non-metal, different property for the two ends. Be careful. And you can see the trend, okay? Going down, 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 going down. Big sharp drop, okay? And reactivity is similar. They can release the electron easily, and then they will be reactive. Change in the property of element and down group includes increasing metallic character of group 1 and decreasing non-metallic character for group 17 elements. Down the group, the number of occupied electron shell increases. Right? For the metal, the free electrons are far away from the nucleus. Attraction force decreases, so reactivity increases. Not so attractive. So the electron will be easier to be removed or be added. So reactivity increases. For non-metal, like halogen, on the opposite. Okay? The number of electrons increases, the van der Waals force increases, so attractive force increases. So that's really to be reactive, so reactivity decreases. Wow, another trend you need to remember. Yes, I know, it's hard. Okay? Not atomic radius, ionic radius, electron negativity first, ionization first, electron affinity, melting point, boiling point. Sometimes increase, sometimes decrease. Crazy, but remember the same rules, okay? The same rules, okay? Across the period, what happened? Same shielding, number of proton increase closer to the octet, right? Down the group, far away from the nucleus, so attractive force decrease. Exception is first electron affinity. It is negative by itself. So more negative is decrease. Less negative is increase. You got it? Of course, okay. So well done, okay, guys, okay. Go full run, okay. And then the trend is hard, but only one explanation for the globe and one explanation for the period, okay. Just remember it, apply it, do the exercise, and you can learn it quickly. Okay? I have confidence on you guys, okay. So if you like our sharing, remember subscribe and then share with your friends, okay. See you for next week, okay. Bye.